That'll show up fairly well. Okay, I've got I've got some of these picked out already. I might have to skip around though, because some of the earlier ones are more involved than others. They're kind of mixed up. So I'll try to pick out the simple ones first and then backtrack. Let's see. This first one is okay. This will be a good one to start with. All right, so we have two balloons, both the same size, and the temperature is the same. So one there, and one there. What does the same size mean? Usually means volume. So that volume and that volume are equal. And we know the temperatures are equal. Okay. One balloon contains hydrogen. Diatomic, right? And the other contains carbon dioxide. Okay. The hydrogen balloon floats and the carbon dioxide balloon sinks in air. Okay. That's based on Archimedes' principle. So what does that mean in terms of floating and sinking? That means the density of this balloon on the left is less than the density of air. That makes it float. The density of this one is greater than air, so it makes it sink. So which balloon contains a greater number of molecules? Well, a clue here. This right here is blue smoke. One second. Notice what we're saying here. If these balloons are the same volume at the same temperature, what's the pressure? The pressure has to be atmospheric pressure, right? Otherwise, we weren't given any other information, so we have to assume that the pressure is also equal. All right? So what does Avogadro say? If that's equal, and that's equal, and that's equal, that's equal. The number of moles of hydrogen is equal to the number of moles of carbon dioxide. It doesn't matter that they float. It just doesn't. To answer the question, all you need to know is these four factors are all equal. So both balloons contain the same number of molecules. All right? The sneaky word problems, they're like that. All right. So I keep readjusting this thing, be sure it stays put. And I'll mark off the ones I do, so I think I'll come back to yeah, I'll come back to number 2. That's a little more involved. So let's see. Let's go down to number 7. Here we go. All right. So I better mark you present first. Here we go. All right, number 7. You have 4 balloons, and each contains 6 grams of a different gas. Now, the problem statement doesn't tell us what the gases are, but the answer to the question does tell us what the gases are. Nitrogen, helium, krypton, neon. Right? So you got 4 balloons, and each one has 6 grams of a different gas. We don't know about the sizes yet. We just know that we have 4 balloons, and I'm just going to do that. They may not be the same volume. And we've got nitrogen in one of them. We've got helium in the other. And we've got krypton here. And we've got neon here. Okay? We do know that each one has 6 grams of these gases. All right. Now the question is, the balloon containing which gas is the largest? So now they want to know what the volume is. Okay, what do we know about volume and the amount of gas? The more moles of gas you have, the more volume you'll have. So if they're all the same mass, which one has the greatest number of moles of gas? The one with the smallest molar mass. Right? The smallest molecule means that it weighs less. So if you're going to have the same mass of each one, then the lightest one has to have more molecules. Right? So which one's the lightest one? Helium. Right? The only one lighter than helium is hydrogen. Helium's the lightest one. It has the most number of moles for the same mass. All right. Let's see. And break up a fight. Okay, I've got 8 marked. Let's see if we should do that one now or later. Let's do that one later. Okay, so we'll skip 8. And let's see, I've got 11 marked. Let's see what it looks like. Okay, this one's simple enough. Let's do number 11. All right. A gas is collected over water at a certain temperature. We looked at one of these Tuesday, I think. So we have a gas that's collected over water. We've got a cylinder here. Probably got marks on it for volume. And then we've got a container of water. And then we have a gas delivery. That. Right. So it makes bubbles, bubbles, bubbles. And it collects up there in the top. Okay. Excuse me. The total pressure in here is 758 torr. Okay. How do we know that? Well, if you lower this cylinder until the level of the water in here is equal to the level of the water out here, then you know that the pressure inside and outside are equal. And all you have to do is take the barometric pressure of the atmosphere, and you know the pressure inside the cylinder. If you try to do it here, then you know that the pressure inside is not the same as outside, because you've got this column of water here also bearing down and adding pressure. So once you drop it down to here, you know the levels are equal and the pressure inside is the same as the pressure outside. So that's how we find the total pressure. What we want to know is the partial pressure of the gas, right? So what did Dalton say? Dalton said that this total pressure is equal to the pressure of the gas plus the pressure of water vapor. You've got two gases in here, the one you're interested in and water vapor. So what does that mean? Well, we need to know what the pressure of the water vapor is to find out the gas, and the problem gives it to you. The vapor pressure of water at whatever temperature it is given as 17 torr. So if this is 17 torr, what's that one? Well, it's 758 minus 17. $741 torr. There it is right there. Okay? All right, that was number 11. Get that one marked off. Let's see, I've also got picked out 18. Let me see how difficult that one is. We might have to come back to it also. Oh, we did one like this from Cengage. So let's do this one again. Of course, it's got different values, but it's the same process. Give us a little practice. 18. Okay. There's a weather balloon. We've got helium in it, and the volume of helium in there is 855 liters. And we're starting at sea level. So we're assuming 1 atmosphere pressure. So our starting volume, wait a minute, what type of problem is this? Is this going to be a state problem, or is it going to be a before and after problem? Well, we're given volume here, and we're asked about the change in volume. Okay. We're also given temperature at sea level that changes from 25 to 15 at altitude. And then we're given barometric pressure here at sea level, and the pressure at altitude is there. So that's a before and after problem. So we need to keep track of volume and temperature, pressure at the different positions. 855 liters is our starting volume. Right. What's our final volume? That's the question. Right? If we're going to find out what the change is, we need to know what the final is and get the difference. So what else do we have? Well, starting temperature at sea level is 25 degrees. Okay. What's the final temperature? 15. Okay. Now let's see what else. Barometric pressure at sea level is 0.947. Atmospheres. Okay. How about altitude? At altitude, the pressure has dropped to 785. Okay. threads on my marker, and it makes it streak. Okay. So now we have all the factors that were given, and we got to decide what equation to use. So if we use the combined equation, because look, we've got variability in more than two. So we can't use individual gas laws. We can't use Boyle's, we can't use Charles, we can't use Avogadro's separately. So we need to use the combined gas law. So P1 V1 over T1. Why don't we put N1 in there? Because the balloon is sealed, right? The amount of gas you started with at sea level is the same at 5,500 feet. So we don't need moles. All right. So we need to solve for V2. Right. So this one comes over here. P1 V1 T2. And then this one comes over here, T1 P2. So let's see, is that right? If we hold this one constant, hold it in position, that one comes over here, 1, 1, 2, yeah. And then this one goes over here, T1 P2. So we've got our equation arranged the way we want it. We just have to fill in the values, but we have to be sure that the values don't need to be modified. So which ones need to be modified? In a ratio like this, the only one that needs to change is temperature. So we need V2 equals pressure volume and T2, 15 plus 273. Then divided by first temperature, 25 plus 273, right? Has to be K. And then second pressure, 785, 0.785. There we go. Now that gives us the final volume. All right, so let me add that one together first. 15 plus 273, right, is 288 K. Then multiply it by 855 and multiply it by 0.947. Then I can move down here, 25 plus 273. That's 298 K. And now to divide that one into this value. Then I divide also by 0.785. So I get rounded off, three significant figures, 997. So at 5,500 feet, the balloon has expanded from 855 liters to 997 liters. What's the change? Okay, so we have to subtract, right? The change equals V2 minus V1, final minus initial. Right? So I just need 855 minus that. And our answer is what? Our answer is in scientific notation, which is okay because I have my calculator set up to give me my answers in scientific notation. So rounded off, I get 1.42 times 10 to the second. Liters. That's the difference, which is E. Right there. Okay, that was 18, right? So let's see. I've got 21 marked. Let's see if 21 needs to be held till later. All right, there we go. All right, let's see, 21. We got a balancing equation. Yeah, we're going to hold that one. We'll come back to that one. Let's see, 23. This is a good one. All right. So you've got a helium balloon and you're out on a sunny day. It says California. It doesn't have to be California. In fact, these days I wouldn't want to be in California. All of a sudden, the temperature doubles. The Celsius temperature doubles. Right? So you've got the beginning temperature is some value, and then the second temperature is equal to T1 times 2, except that this is in degrees Celsius. Degrees Celsius. Okay, that's an important distinction. Which of the following are true? The actual temperatures are needed to answer this question. Well, maybe yes, maybe no. If you're before and after, they're going to be ratioed, right? Ratio one to the other. So you don't have to know the temperature. You just have to know what the ratio is. So if we're looking at a combined gas law, right? Well, we know that moles didn't change. Right? Because the balloon is sealed. How about the pressure? Pressure didn't change. Well, it didn't say that it changed, so we can assume that the pressure stayed constant. Right? So now we know that the volume temperature relationship is the one we're focused on. And that's Charles' law. Let's rearrange that. Right? Let's put this one over here and that one over there. T2 over T1 equals V2 over V1. Right? So that ratio, we do know what that ratio is. Right? T2 is equal to twice T1. So this is equal to 2 times T1 over T1, which means that this is equal to 2. If the temperature is in Kelvin, right? This is only for Kelvin. So what would this ratio be if we converted it to Kelvin? Well, this one would be T2 plus 273 And this would be 2 times T1 plus 273. All right. So the ratio then would be, let's divide both sides by this value. Now let's divide both sides by this value. Right? So that puts this one over here, this one over there, makes that 1, and this one is 2 times T1 plus 273. Okay, so this is 2 T1s plus for 546. Okay, that's kind of difficult to follow, so I'm going to not rely on this one. Let's just erase that. The ratio of degrees Celsius is 2 to 1. That's obvious. But is that the same ratio as Kelvin? Well, if you add 273 to this one and 273 to that one, then the ratio is no longer 2 to 1. The ratio is a lot less than 2 to 1. So the first statement, the actual temperatures needed to answer this question, no, that's false. We can answer that question simply by the ratio. How about the volume of the balloon will slightly increase? Right? If this is true, and we add 273 to it, is the ratio still 2 to 1? No, because this is a very slight increment compared to 273. Right? Let's just pick a number. Right? What would be a realistic? Say 20 degrees to 40 degrees. So if this were 20 degrees and this were 40 degrees, that would be double Celsius. Right? So this one would be 313. And this one would be 293. Is that 2 to 1? Right? 2 times 293 is a lot bigger than 313. So this is a lot less than 2. So the volume is not going to increase double. It's not going to double. It's only going to be a slight increase. Right? So B is true. The volume of the balloon will slightly increase. How about the pressure inside the balloon? Well, the pressure inside the balloon is going to be balanced by the pressure outside the balloon, right? That's false. How about the volume of the balloon will decrease? No, we just said it's going to increase because the temperature increased, right? So D is false. How about the volume of the balloon will double? No. We already said the volume of the balloon can't double because the temperature did not double. The Kelvin temperature did not double. So the only one that answers this question adequately is B. The volume of the balloon will slightly increase. All right, let's see, it's still centered. That was 23. Let's see, I got 24 marked too. Let me look at it. 24 is a good one. We can do that one right now. All right. Which of the following statements is true of 19 grams of fluoride gas at standard temperature and pressure? So we have a mass of 19 grams of fluorine gas at standard temperature and pressure. Okay, so let's take each of the statements. Well, first of all, what else can we derive from that, right? If we have 19 grams of fluorine gas, each fluorine is 19 grams. So 1 mole of fluorine would be 38 grams, right? So how many moles is that? That's a half a mole of fluorine gas. Okay, we may need that, we may not, but we do know it's true. So let's look at the possibilities. Okay, it contains the same number of molecules as half a mole of oxygen at STP. A is true. A is true. So E can't be right. None of the above? At least one of them is true. How about B? It exists only in the form of ions. Well, that's kind of ludicrous. These are all molecules, fluorine molecules. If it reacts with a metal, yeah, then you'll make ions, but then you won't have a gas anymore. So B is false. How about C? It occupies a volume of 22.4 liters. At standard temperature and pressure, which is what? 0 degrees C and 1 atmosphere. That's for gases. How many moles does it take to make 22.4 liters? That's known as the molar volume of gas at standard temperature and pressure. 22.4 liters is 1 mole, right? We've got half a mole, so we really only have 11.2 liters, right? So that's false. How about D? It contains 6.02 times 10 to the 23rd molecules. That's 1 mole, isn't it? Right? So D is false. Because we only have half of that. We've got 3.01 times 10 to the 23rd molecules. So the only one that's true is A. Okay, that was 24. Let me mark that one off. And the next one I got marked is 28. We can do this one. 28. All right. So let's see. What type of problem is this? This is one referencing gas laws, it looks like. Because I don't see any reactions or partial pressures. So it has to be one of the laws or a combination of the laws. So let's see, is this before and after, or is this a state? Compressed gas cylinder at 137 atmospheres, which is pretty high, at 23 degrees, is in a room where a fire occurs. I think I want to get out of there in a hurry. The fire raises the temperature of the gas to 475 degrees C. What's the new pressure in the cylinder? Well, let's hope the new pressure doesn't exceed the limits of the cylinder. All right, we're given 137 atmospheres. This is a before and after. 137 atmospheres at this temperature, 23 degrees. Right, we know we're going to need Kelvin, so we might as well do it now. Okay, and then a fire raises the temperature to 475. They want to know the pressure. So this one has to be also Let's see if I can do this one. 8, 14, 1, 6, 7. There we go. So, what's the relationship? If the temperature goes up, the pressure goes up, right? There's not one law that we've studied that covers that. It's the combined gas law. So if we know P1 V1 over N1 T1 equals P2 V2 over N2 T2, then now what we have to do is say which ones are constant. The moles don't change, and the volume doesn't change. Right? The cylinder is sealed. So the ratio is P1 over T1 equals P2 over T2. So we solve for P2. Right? P2 is going to be P1 times T2. Divided by T1. Okay? So now we can put in our numbers. 137 atmospheres. T2, 748, and 296. And that will give us the new pressure in atmospheres. All right, 137 times 748 divided by 296. Rounded off to 3 places, 346 atmosphere. That's a lot of pressure, but I think the cylinder can hold it. Those cylinders have safety factors built in. All right. Oh, so that is, well, scientific notation right here. 3.46 times 10 squared atmospheres. That was 28. All right. Okay, we're still good. Let's see. I got 29 marked. Let's see if I can, if this is not too complicated. Which of the following statements is true about the kinetic molecular theory? Okay. 29. And we're talking about the kinetic molecular theory. All right. Let's see. Is A true? Pressure is due to the collision of gas particles with the walls of the container. That's as true as it gets. That is a definition. That's one of the postulates of the kinetic molecular theory. So A is true. How about B? Well, it doesn't say 2 of the above, 3 of the above, all of the above, none of the above, anywhere else. So we found our answer. But let's look at the others just for fun. Gas particles repel each other but do not attract one another. B is false. Why? Because one of the postulates of the theory is that gas particles do not interact. They don't attract, they don't repel. They act like billiard balls. They just bounce off one another with 100% elastic collision. How about C? At least 2 of these statements are correct. Oh, I didn't see that one. So we do need to look at all of them, right? We can't answer C yet. We have to look at D and E. Okay, so how about D? we'll hold C till later. The volume of a gas particle is considered to be small, about 0.1 milliliters. All right, that's another postulate, but that one's false. The volume of a gas particle is considered to be 0. It's point volume. That is, it has no volume. How about E? Part of that statement is true. It's considered to be small, but it's so small, it's non-existent. E, adding an ideal gas to a closed container will cause an increase in temperature. Adding an ideal gas to a closed container, that may be true, but the kinetic molecular theory says nothing about that. It doesn't say that you're going to get a change in temperature when you add gas. All it says that you're going to increase the number of collisions and you'll increase the pressure. It also says that the temperature is a measure of the average kinetic energy of the molecules in the container. Let me say that again. The temperature is a measure of the average kinetic energy of all of the molecules in the container. That's all it says about temperature. Doesn't say anything about what happens if you add. Now, other gas laws do, right? Combined gas law will say all of the factors being equal, let's see, is that true? We're going to change the mole, so we keep that one. Temperature we want to keep there, right? We're going to let pressure be constant, so it's got a movable piston. And the volume's going to change accordingly. So what happens if you add moles? Right? If you double the moles here, then you have to decrease the temperature, right? So that doesn't make any sense. Point is, the kinetic molecular theory doesn't say anything about that. All right, so C can't be true. The only one that's true is A. Let me check something for just a second. 29. Let me see what I said in the work problems. Maybe I'm missing something. Yeah, that's fine. I'll go with what the explanation I gave. And 29, mark that one off. I also have 30 marked. Let's see. Consider a reaction of magnesium metal hydrochloric acid, blah, blah, blah. Okay, we'll come back to that one, because that involves stoichiometry. I want to get all the gas laws out of the way first, and then we'll come back to stoichiometry and work these problems. So the next one I have marked is 34. Okay, 34 is actually an expression of one of the gas laws. If the temperature and the pressure are held constant, remember, if you have pressure, temperature, volume, moles, and it says you hold pressure and temperature constant, right? Pressure and temperature are constant. So we're looking at volume and moles. So whose law is that? That's Avogadro's law. And what does it say? They're directly proportional. If you increase the number of moles of gas, you increase the volume. All right, so which one speaks to that? They're directly proportional. Volume and number of moles of gas are directly proportional. That is Avogadro's law. Volume, and the fancy symbol we use for that is proportional to moles. Right? The law actually says this. That ratio is a constant. So remember, whenever you have a quotient is equal to a constant, they're directly proportional. If this one goes up, that one has to go up in order to maintain that constant. All right. Okay, so let me mark that one off. That was 34. Let's see. 37. 37 is doable. All right. Perform the following conversion. All right. You're starting off with 1.177 atmospheres. And the problem wants you to fill in this blank for the number of torr. So you need a conversion factor, right? Starting here, you're ending up here. So do we have a single factor that will leave us with torr and cancel atmospheres? In fact, we do. 1 atmosphere is equal to 760 torr. So 760 times 1.177, we might be able to do this one. All right, it's not going to be this one, right? 760 times won't be that one. Is 760 times 1? No, that's not big enough. How about this one? 760 times 1.1, it should be greater than 760. So that was not right either. This one's 10 to the minus 3, which is a very small number. That one won't be it either. So by process of elimination, 894.5 should be the answer. And in fact, it is 894.5. Four significant figures, 4 significant figures. Okay? So on a test, maybe it's quicker just to say eliminate the obvious wrong answers and you're left with the right answer. All right. Let's see. That's good. That was 37. Let's see. The next one I have marked is 43. 43. Here we go. Okay. We can do this one with gas laws. All right. So a sample of argon gas occupies a certain volume, whatever that volume is, at 15 degrees. Okay? At what temperature would the volume of the gas be 3 times as big? So we want to know this one, but we're given this one is equal to 3 times as much. Okay? So we have a relationship here, temperature and volume. And we're also told that the pressure remains constant. The number of moles remains constant because it's confined. So if the pressure is constant, then what ratio do we have? We have that one. Out of the combined gas law, that one remains. So we want to find out what this one is. Is that right? Bring this one over here. That one goes over there. This one goes over here. All right. So the answers are in Celsius, but we can't do the calculation unless we use Kelvin. That means we've got to work it. Convert to Kelvin, work the problem, and convert back to Celsius. So this temperature is going to be volume. Volume 2 is 3x. Temperature 1 is 15 plus 273. And volume 1 is x. Okay? So the x's cancel. So we got a 1 down here, we got a 3 up here. So this temperature is going to be in Kelvin. 3 times 15 plus 273, and then divided by 1, which is 864 K. So we need to subtract 273 from it. And I get 591. And there it is right there. Okay? All right, that was 43. So let's see, what's the next one I have marked? 49. Let's see what 49 is, if it's workable at this point. Whoops, too far. 49. Which of the following will give a graph with a straight line and a y-intercept of 0? Okay. You need a straight line and you need a y-intercept of 0. Okay, so how do you get a straight line? Well, you need either a negative slope or a positive slope, but you also need a direct, actually you need a direct relationship. They need to be directly proportional values. What happens if they're inversely proportional? For instance, Boyle's law. What kind of graph do you get there? You get a hyperbola. So remember how we made a straight line out of that? We transform the volume to 1 over v. Right? If we say divide both sides by v, equals k divided by v equals k times 1 over v. So there's y equals mx plus b, and b is equal to 0. Goes through the origin. Right? So that would be one, that's a possible answer. If we find plotting pressure versus 1 over volume will give us a straight line. So let's see. Here we go again, 49. Volume versus temperature in degrees C. What happens when you plot volume and temperature in degrees C? Right. So you have volume here, temperature there. You get a straight line, but the y-intercept is not the origin. Right. The only way that you would get a y-intercept to be the origin is if the temperature were in Kelvin, right? Because Kelvin takes you out here. Now the y-intercept is 0. But for C, it's not, right? So A cannot be true. Volume versus 1 over temperature in K. Well, that's just crazy. If you plot volume in K and temperature, see, volume and temperature are proportional, are directly proportional. If you take the inverse of the temperature, now you're back to the hyperbola situation. You're going the wrong direction. How about volume versus temperature in K? Aha. There you go. The y-intercept now is 0. If the temperature is in K, that is a true statement. Volume versus 1 over temperature. No. Pressure, well, actually those have nothing to do with it, right? Because all the answers are volume and temperature, right? So volume versus 1 over temperature will get you to the same wrong answer, well, a similar wrong answer as B. You're going the wrong direction. Volume and temperature are directly proportional. The only way that you can get a y-intercept of 0 is if the temperature is actually Kelvin. If you plot Celsius, you won't get an origin intercept. So the answer is C. Okay, let's scoot this back where it's lined up. There we go. That was 49. Let's see. 52, I think, might be. Oh, we can do 52. Yeah, 52. So let's just read through it, and then we'll say, what's the question and what are we given? Solid carbon dioxide is placed in a Ziploc bag. That sounds like fun. At a certain temperature, solid carbon dioxide sublimes. It turns directly from solid to gas. And that temperature is anything above minus 78.5 degrees Celsius. Anything above that, it will sublime. But it does this at that temperature. It changes from solid to gas at a rate of 0.726 grams of solid every minute, converted into gas. Okay, that's the rate at that temperature. How many gaseous carbon dioxide molecules are present after 4.84 minutes? All right. This is dimensional analysis. The question is, how many gas molecules are there? Right? So we have to know how much of the solid carbon dioxide is converted into gas, right? And we have a measure. For every minute, they're about 3/4 of a gram converted. So 0.726 grams per minute and how many minutes? 4.84 minutes. So now we can find out how many grams were converted in that amount of time. 0.726, is that correct? 726. And 4.84 times that value. We have 3.514. I'm going to keep an extra decimal. 3.514. All right. Now, how do we get to molecules? We've got to convert that to moles, right? Before we can count how many molecules. So what do we need? 3.514 grams right? Molar mass, correct? So what's the molar mass of carbon dioxide? Well, let's see, there's one carbon, 12.01, and 2 oxygens, 16 each would be 32. So that's 44.01. That's how many moles of carbon dioxide we have. How many molecules is that? .022 times 10 to the 23rd. Cancels moles, leaves us with molecules. Okay, that should answer the question. So, 3.514, let's see, divided by 44.01 and times 6.022 times 10 to the 23rd. I get rounded off, let's see, 3 significant figures, 4.81 times 10 to the 22nd molecules. Let's see, is that one there? Yep, there it is right there. 4.81 times 10 to the 22. See, that was just dimensional analysis. Keep track of your units. All right, that was 52. Let's see, 55. The air in an inner tube, let's see if I can just convert it. Yeah, we can do this one. This is a unit conversion. Let's go. What did I say? 55. All right. The air in your inner tube of the tire of a racing bike has a pressure of 116.8 psi. That's a lot. That's a lot of pressure. But those are very narrow tires, and they do that to minimize friction with the ground. I used to have a 10-speed bike, and I think the pressure in that one was only 70 psi. Still pretty high, but it was nothing like a racing bike. So it just says convert this pressure to atmospheres, right? 116.8. 116.8 psi. What is that? Pounds per square inch. Right, we want to convert it to atmosphere. So what's the relationship here? Well, you could use one of two. It depends on how many significant figures you want. 14.69 or 14.7 will probably work. We'll just do it this way and see. So we'll divide 116.8, 14.69 divided into it. I get 7.951. 1, 2, 3, 4 significant figures. 7.951. Let's see. Do we have something close? There's something close right there. 7.946. My guess is if we used 14.7 here, I bet we get that answer. $7.946. All right. So in that case, if you use that one, then you come close and you pick the best answer. And the best answer is 7.946. All right. That was 55. Next one I have marked is 60. All right there. Let's see. You're holding two balloons of the same volume. One balloon contains 1.05 grams of helium. The other balloon contains neon. What's the mass of the neon in the balloon? Of the neon balloon? Simple. All right. 60. All right. We have two balloons. Same volume. One balloon has 1.05 grams of helium. Helium, 1.05 grams. And the other one has neon. And we don't know the mass. Okay? Now we have to assume that other things are equal. The volume's equal. The temperatures should be equal. We got both of them right here in close proximity. The pressures are equal. So what do we know? The number of moles are equal. So the moles of one are equal to the moles of the other. Okay. So if this helium balloon weighs 1.05 grams and we got the same number of molecules in there, then how do we find the mass of that one? Well, two possibilities. You can go the long way around the barn, convert that to moles, and say that moles is equal to this moles, and then convert that back to grams. Right? But we know that the ratio of the two, since they're equal moles, then the ratio of the molar masses is equal to the ratio of the moles, is inversely proportional to the moles. So this is going to have a certain number of molecules. This one will have less. Right? So our ratio, well, let's do this bona fide mathematical. So this has a molecular weight of something, and this one has a molecular weight of something else. Okay. So we know that these two are equal. Right? So how do you get moles? You get moles. Right? Let's see. Molecular weight equals mass per moles. Right? So moles is equal to mass divided by molecular weight. So this one will be, let's change these right here. In fact, let me move it up here. So the helium moles are equal to the neon moles. But we know that the ratio is mass, the mass of helium divided by the molecular weight of helium is equal to the mass of neon divided by the molecular weight of neon. There you go. So now we have a handle. We've got mass in our equation. So what's the molecular weight of helium? Well, let's say, what's the ratio? Helium is about 4. Neon is about 20. So that's 5 times. This molecular weight is equal to 5 times the molecular weight of helium. Right? So we can substitute that in here. All right, I'm going to have to erase some of this. Right, now that we know that this goes in here, we can say mass of helium divided by the molecular weight of helium is equal to mass of neon divided by 5 times the molecular weight of helium. Okay? These two are going to cancel. What were we looking for? What's the mass of the neon? We're looking for this one. So let's solve for that one. Mass of the neon is equal to 5 times the molecular weight of helium times the mass of helium divided by molecular weight of helium. Right. These two cancel. So the mass of the neon is going to be 5 times the mass of the helium. So if this one is equal to 1.05, 5 times 1.05, I should be able to do that in my head, is equal to 25.25 grams. That's the mass of the neon. I don't see it anywhere in here. What's the mass of neon in the balloon? Well, maybe I used the wrong ratio. It's approximately 5. The closest answer would be this one, 5.29 grams. Oh, duh. I amaze myself sometimes. 5.25 grams. So the closest one is A. I don't know how I got that other one. Brain farts, whatever. It was wrong. 5.25, or the best answer, 5.29. Is there any question about that one? Since they have exactly the same number of molecules, then the only difference is how big are the molecules relative to one another. Neon is 5 times as big as helium, so the mass should be 5 times in that neon balloon. So that's why I went through all that to prove that it's just 5 times. All right, 67. Let's see what 67 holds. Okay, a hydrogen balloon at 25 degrees Celsius, 1 atmosphere, has a volume of 1 liter. How many grams of argon gas must be added to the hydrogen balloon to achieve a volume of 3.78 grams of liters at constant temperature and pressure? We should be able to do this one. Okay, that was 67, I think. Yep, 67. All right. So a hydrogen balloon, so you got a balloon that's going to expand. A hydrogen balloon here, this is before. The hydrogen balloon at 25 degrees and 1 atmosphere pressure. Okay, and a volume of 1 liter. And there we go. So that's V. Okay. How many grams of argon gas must be added to achieve a final volume of 3.78 liters? Now we have hydrogen plus argon. And we want to know the mass of this one. So that's before, and this is after. Temperature is the same. Right? Didn't it say that? Constant temperature and pressure. Pressure is the same. So we only have a difference in volume and moles. That's Avogadro's law. So we got this one, volume of hydrogen divided by moles of hydrogen equals the volume of both divided by moles of both. Okay. So what do we need to know in order to calculate the mass of argon? We need to know the moles of argon that were added. Right? So if this is the total moles, if we find out the total moles, then we can subtract these moles and find out how many moles of argon there are. Okay. So the volume here is 1 liter. And the moles of nitrogen, well, we don't know that. Hydrogen, excuse me. Moles of hydrogen equals 3.78 liters over moles of hydrogen plus moles of argon. Okay, we've got an equation in 2 unknowns. Can't solve it. So what are we going to have to do? We're going to have to find out how many moles of hydrogen there are. That means PV equals nRT. So number of moles equals pressure, volume, RT. Yeah. Okay, so what's the pressure? 1 atmosphere. What's the volume? 1 liter. 0.08206 for R. And the temperature is 25 plus 273. Okay, so let's see, how many moles of hydrogen do we have? That's 0.08206 and 25 enter 273 plus times that, and then we divide it into 1. 4.089 times 10 to the minus 2. That's how many moles of hydrogen we have. So this, we substitute 4.089 times 10 to the minus 2. Do the same thing on this side. 4.089 times 10 to the minus 2. Then we can find out how many moles of argon were added. So, I need some room to calculate here. All right, so what's 1 divided by 4.089 times 10 to the minus 2? Is 24.45. So this term is 24.45. This side is 3.78 divided by 4.089 times 10 to the minus 2 plus moles of argon. So we need to make this one times that one. All right, so this 4.089 times this one is 1. Well, of course it is, because we just divided it by 1. And that's plus 24.45 times the moles of argon equals 3.78. Okay, so now we have 24.45 times the moles of argon equals this one minus that one. Now this one is equal to this term. .78, 24.45 is 1.137 times 10 to the minus 1. What did I say? 137. Okay, now we just have to convert that to mass. We use argon, the molar mass of argon, grams per mole. So times that, argon is 39.95. Moles cancel. And I get 4.54. Grams of argon. There it is. Now I can't help feeling that there's an easier way to work that one. Let me see how I worked it before. 67. Yeah, I did it the hard way. Let me do it again the easy way. All right, what do we know? We know that we're starting off with 1 liter of gas. And we're going to end up with 3.78 liters. So what's the volume of argon that was added? That's the volume of argon. And these gases behave independently. Right? Dalton proved that. 2.78 liters. Pressure is 1 atmosphere. Volume is still 1 liter. 0.08206. Pressure, volume. No, liters. Excuse me. Pressure, volume. Volume is 2.78 liters. There we go. And temperature is, 25 plus 273. There we go. Now that gives us the number of moles of argon, quick, fast, and in a hurry. (1.137 times 10 to the minus 1). Moles of argon. Then all we have to do is multiply it by its molar mass, and we get 4.54 grams. Right. So that was the quick way. I did it, but I had to go around the barn 3 times. When all I had to do was open the door and walk through to the other side. Let's see, that was 67. 74. 74, here we go. Let's see, a partially filled party balloon with 2 grams of helium gas. Where's the question? How many times bigger is the party balloon? Okay, we've done something to it. You add 3 grams of hydrogen to the balloon, assuming constant temperature and pressure. How many times bigger is the party balloon? Comparing before and after the hydrogen gas has been added. Choose the best formula to use to solve this problem. All right. So let's see what we're given. Partially filled balloon is 2 grams of helium gas. Mass of helium is 2 grams. Okay. The mass of hydrogen is 3 grams. All right. Constant temperature, constant pressure. Temperature, pressure, constant. So what are we dealing with? We're dealing with volume and moles. So the before and after, the before is just the helium. Right? Volume of helium divided by moles of helium equals what? The after is volume of helium plus hydrogen divided by the moles of helium plus hydrogen. Okay. Let's see. All right. So if all we have to do is pick out the formula, which one satisfies? Let's process of elimination. A. Volume temperature relationship. No, temperature is constant. That one's false. Won't do. How about B? Pressure and moles. Pressure is constant. That's not going to change. How about C? Volume and mass. Volume versus mass. Is there any way that formula will not give you the right answer, because the relationship of volume to volume is not based on mass. It's based on moles. So this one is false also. How about D? Volume in moles. There it is. That's true. Pressure, volume. Pressure is constant. E is false. So D is the one you want. And the way you would do that is you would convert helium gas to moles. You would convert hydrogen to moles and add it to the helium moles for this one. So you'd have this one, you'd have this one, you'd have that one. Then you could solve for this one. Okay? But the mass in and of itself does not give you the answer. Only the moles. So that's why the answer to this one is D. All right, let's see. Get that straight. All right, that was 74. 78, I think we can do that one. Which conditions of pressure and temperature are most ideal for a gas? You just have to memorize this one, right? What did I say in class? In order for a gas to be ideal, we have to minimize the effect of individual gas molecule volume, which means the lower the pressure, the fewer the molecules. Right? So low pressure approaches ideal behavior. Then we also have to minimize the interaction of the molecules. In other words, they can't attract, they can't repel. So the way you do that is you increase the kinetic energy of the molecules. So that they're moving so fast, their encounters are very brief, and it comes and goes like that. The way you do that is high temperature. Okay? Low pressure, high temperature gives you ideal behavior. Now, how does that relate to gases around us right now? At room temperature, right? Room temperature is high. Compared to what? Compared to 0 K. Compared to absolute zero, 273 is high. Well, 273 plus, say, 20, 293. 293, 298, that's high. Okay, how about low pressure? 1 atmosphere is low pressure, or anything less than that. Even a little bit higher than that would be low pressure. In order to have high pressure, you need to be 2, 3, 4 orders of magnitude higher than that. Like 100 atmospheres, 200 atmospheres, 800 atmospheres, in order to start introducing non-ideal behavior. Oh, so that was A, low pressure, high temperature. All right, so that was 78, 79. All right, we did one of these in Cengage, and I'll get back to that one in a second. I want to finish, I want to go all the way to the end with the ones I've selected. Okay, Let's come back to 81 in just a second. Let's do 82. 82. Let's do 83. And then we'll come backwards. 83. All right. Suppose you have a balloon that has a volume of 7 liters. Okay. Each time you blow into a balloon, well, okay, this is the volume of each balloon that you blow up. Each time you blow into a balloon, you expel. Now this is, excuse me, this is a single balloon, and you're going to blow into it 0.045 moles of air each time you exhale. So you have 0.045 moles of air per breath each time you breathe out. How many times can you blow into the balloon before the balloon pops? If its maximum volume is 7 liters. Assume atmospheric conditions of 1 atmosphere and 22 degrees, and that your breath is room temperature. All right, if we blow this much out with each breath, let's see, that's going to be so many moles of air, and the pressure and temperature are constant. Temperature and pressure do not change. So that means moles and volume are proportional. Oops, that didn't make any sense. There we go. So each time you blow in 0.45 moles of air, what volume is that? We might have to do ideal gas equation for this one. I don't think we can do it proportionality. So what is the temperature? The temperature is 22 degrees, and the pressure is 1 atmosphere. Right? So each time you blow in this many moles, what volume is that? So N equals PV over RT. That's not what we want. We want volume. So volume equals nRT over P. Okay, the number of moles per breath. We're going to find out the volume per breath. The number of moles is 0.045, 0.08206. Temperature is 22 plus 273. And pressure is 1 atmosphere. Okay, so now we're going to solve for volume. So that's 1.089. 1.089 liters per breath. Okay. So if that's how many liters per breath, how many breaths can you put into it before it pops? Well, use that as a conversion factor. You have 1.089 liters per breath Divide 1.089 into 7, and you get 6.43. 6.43. Okay. So you can put 6 breaths in there, and the balloon will not pop. If you put 7 in there, it will pop, because that exceeds the volume. 7 breaths will give you the next increment, and it's too big. Right? 1.089 on that would be 7.52 liters with 7 breaths. So 6 times and it won't pop. All right. So let's go backwards now. Let's see. We mark this one off. Backwards to 82. There we go. And we got plenty of time. All right. 2 liters of NO, nitrogen monoxide, at 1 atmosphere and 25 degrees C is reacted with 1 liter of hydrogen at 2 atmospheres and 25 degrees C, according to the following unbalanced equation. Do we have a limiting reactant? Which, if either, is limiting? All right, so here's your equation. This is a stoichiometry problem, so you have to have a balanced equation. So we need NO plus H2 yields N2 plus H2O. All right. So let's see. We have 1 nitrogen here and 2 there. Now we have 2 oxygens here, and we need 2 oxygens there. But now we have 4 hydrogens. Okay? So let's see. Is that balanced? 2 nitrogens. Yep. 2 oxygens. Yep. And 4 hydrogens. Yep. We're balanced. Okay, now what are we given? 2 liters of NO. 2 liters of NO at 1 atmosphere pressure and 25 degrees, which is the same for both of them. 25 degrees, 25 degrees. Okay, how about hydrogen? We're given 1 liter of hydrogen and 2 atmospheres. Okay, that's all we're given. So is there a limiting reactant here? All right. How many moles do you have here? Well, we could calculate the moles, but all we need to know is, are they equal number of moles, or is one of them greater than the other one? Right. So what do we know? Pressure and volume. Pressure, volume. For this one is 3 liter atmospheres. What about this one? 1.0, excuse me, 1 times 2 is 2. And this one is 1 liter times 2 atmospheres equals 2 liter atmospheres. So what does that tell us? That tells us we have exactly the same number of moles in each one. Why? Because pressure times volume is constant. Right? Pressure times volume equals constant. They're both the same. So what does that mean? That's Boyle's law. And Boyle's law only works if the temperature and the moles are both constant. So we know that we have the same temperature, and we know that we have the same moles. So there is no limiting reactant. This is a stoichiometric mixture. No limiting reactant. All right? That's the key. Recognizing that this is Boyle's law, and these have to be constant. So if these are the same, those must be the same also. All right. So that was 82. 81. 81 is going to take some work, but it's doable. Right? 81. 15-gram sample of a hydrocarbon is placed in a balloon at 1 atmosphere and 25 degrees Celsius. The volume of the balloon is 12.2 liters. All right. The hydrogen is 79.89% carbon, 20.11% hydrogen by mass. Determine the molecular formula. All right, this is going to take a little work, but break it down. How do we determine molecular formula? You have to do the empirical formula first. So what's the empirical formula? Carbon, 79.89%. Hydrogen, 20.11%. All right. What do we do with that percent? We assume that the sample is 100 grams, which means that makes this grams and grams. Now you have to convert them to moles. Right? Because empirical and molecular formulas are based upon numbers of atoms, not mass. Right? So this one is 1.01 for hydrogen and 12.01 for carbon. Right? So we get that ratio, and that ratio is the moles of carbon to moles of hydrogen. 79.89, 12.01, so that's 6.65. Moles. And hydrogen is 20.11 divided by 1.01 is 1.99. Okay, we need a whole number. This one's about 2, but this one is 6 2/3. Okay. So this is 2, and this is 6 2/3. So how do you get rid of that 2/3? Multiply by 3. Right? So 3 times this, 3 times that, 3 times this is 6 plus 2 is 8. Correct? And this is 6. So the empirical would be 8H6 But the empirical formula has to be the simplest whole number ratio. So what can we do? We can divide 2 into this and 2 into that, correct? Let's see, did I do that right? 79.89 grams carbon, yeah. All right. Okay. So this would be 343, C4H3. There's something wrong with this picture. What did I do wrong? Well, we're given 15 gram sample, right? And I assumed 100 grams. Let's back up. Let's use the actual values. So if this is percent, and that's grams per 100 grams. So this would be, well, percent is what? Percent is equal to mass of carbon divided by the total times 100. So 100 divided into this times the mass of carbon, or the times the mass of the sample. Actually, the total sample, yes, the total sample would go over here also. That would give you mass of carbon. Okay. So I'm starting all over again, actually. 79.89, 100 divide times 15 is 11.98 grams. And 15 times the other one is 3.017. There we go. Now let's convert those to moles. Okay, so carbon is going to be 11.98, enter 12.01 is 0.998 moles. And hydrogen is going to be, well, that's about 3. So this is 1 to 3. Carbon, hydrogen, there we go. Okay, that's our empirical formula. Right? So now we need to do what else do you need? You need the actual molar mass of the compound. Right? The empirical weight for this one equals 12.01 plus 3.03 equals 1504. Grams per mole. Okay? So what is the molar mass? Well, what do you need to know the molar mass for this compound? There's your multiplier. The molar mass is equal to mass per moles, right? So do we have a mass? Yeah, we got 15 grams. We know that. How many moles do we have? That's the question. For a gas, we need this. moles equals PV over RT. All right. What's the pressure? 1 atmosphere. What's the volume? 12.2 liters. R and temperature. 25 plus 273 is 298 K. Okay. So how many moles do we have? Let's see. 12.2 divided by 0.08206 divided by 298 is 0.499. So our molecular weight is equal to 15 grams per 0.499 moles. Well, that's about 30. Let's see exactly what it is. Yeah, 30.1. All right, so if the molecular weight here is 30.1, what is X? Well, if we multiply by 1, we still get 15. If we multiply by 2, and this has to be a whole number, if we multiply by 2, we get 30. So X is 2. So if X equals 2, then our molecular formula is C2H6. Okay? That was 81. Let's see, we're good there. And let's go backwards. 79. We'll come back to 79 because it uses a similar type of calculation that we just used on that other one. So was 11. Yeah, we only got 45 minutes left. So we might come back to 79. Let's back up to we did that one. Ooh, we gotta go way back up to the top. Here we go. 30. We skipped 30. There we are. Okay. Consider the reaction of magnesium metal with hydrochloric acid to produce magnesium chloride and hydrogen gas. So you're given the reactants and the products. You just need a balanced equation, I think, because if 3.02 moles of magnesium and 3.02 moles of hydrochloric acid are reacted, how many liters of hydrogen gas are produced at 1 atmosphere and 49 degrees Celsius? So we do need a balanced equation. So we got magnesium, let's see, 30. Magnesium plus hydrochloric acid yields, that's magnesium solid and hydrochloric aqueous solution, and produces magnesium chloride, 2, right? Chlorine is -1, magnesium is +2, and hydrogen gas. Okay, let's balance. 1 magnesium, 2 chlorines. So that's 2 hydrogens, 2 hydrogens. We're balanced. 1 coefficient changed, and we're done. Okay, now what are we given? 3.02 moles of magnesium and 3.02 moles of hydrochloric acid. Okay, what else are we given? We're given, let's see, 1 atmosphere pressure, okay, and 49 degrees C. All right, so we just need to find out how many moles of hydrogen are produced. Well, remember, if you're given exact amounts of both reactants, one of them is going to run out. So we need to say which one runs out. Well, for every one of these, you need 2 of those. All right, do we have 2 of those? No, we've only got 1 of those. So for every 2 of these, you need 1 of those. So half of that is what you need of this one. This one is excess. This one runs out. Right? So this is going to produce how many moles of hydrogen? Half that much. Well, we could have said that this is 1 to 1. So if this is half of that, then that's equal to half of that. So it's let's see, what's half of that? 1.51 moles of H2. All right, now we can determine how many liters. We know the moles, we know the pressure, we know the temperature. So volume is equal to moles RT over P, which is what? 1.51 moles times our gas constant times temperature, 49 plus 273, divided by pressure, 1 atmosphere. Okay, so 1.51, 0.08206, and 49 under 273 plus and times that. So I get 39.9 liters. And there it is right there. Okay. That was number 30. All right, move this back just a hair. There we go. That was 30, mark off 30, here we go. Now let's go backwards a little more to 21. All right. Okay. 21. Consider the following unbalanced equation. Now, are we going to need to balance it? Let's see. 1.55 grams of ethanol, that's this compound right here, reacts with 10 grams of oxygen. What's the total volume of gas present after the reaction is complete? Assuming the temperature is 1 atmosphere and 25 degrees C. What's the total volume of gas? All right. Let's balance the equation. Ethanol plus oxygen yields carbon dioxide and water. Okay. Now, we might have to do a budget for this one. So carbon, hydrogen, oxygen. We have 2 carbons. We have 6 hydrogens. We have 3 oxygens. On this side, we have 1 carbon. We have 2 hydrogens. And we have 3 oxygens. Yep. Okay. We don't need to mess with the oxygens, but plus it's a single element, so we don't want to touch that one yet. How about carbons? Let's just start with carbon. 2 carbons makes 2 here, and that changes the oxygens to 5. Okay. Hydrogens. We have 6 hydrogens here, so we need 6 hydrogens here. Okay. That changes the oxygens to 3 plus 4 is 7. Okay. So now, how do we get 7 oxygens here when we've got them in 2 places? Well, there's going to be 1 here, right? So we need 6 more oxygens. 6, 7. So that should be balanced. 2 carbons, 2 hydrogens. 6 hydrogens, 6 hydrogens, oxygens. 1 plus 6 is 7. 4 plus 3 is 7. So that's the balanced equation. Now we can work our problem, stoichiometry. 1.55 grams of ethanol. Okay? Reacts with 10 grams of oxygen. Okay? What's the total volume of gas? So we're aiming at carbon dioxide. This is gas. This is liquid. So we're aiming at this one, and this one's gas. So if we have any left over here, then we have to add it to the volume of that one. What if we just determine the total number of moles of gas? How about that? So if we convert this to moles and that to moles, we're going to have to do that anyway, aren't we? In order to determine limiting reactant. So what's this one? Times that. So what's the molar mass of ethanol? 2 carbons, 12.01 times 2, and then 6 hydrogens, 6.06, and then 1 oxygen, 46.08. Pardon me for a second. I got to let a cat out of my office. Kitties. Come on, kitties. Here you go. How'd you go? Go, go, go. You too. Go, go. Here we go. Now, back to our problem. So how many moles is that? 1.55. 1.55 divided by that number. I get 3.36 times 10 to the minus 2. That's how many moles of ethanol. How many moles of oxygen? Well, 10 grams, right? 1 mole. How many grams is oxygen? 16 times 2 is 32. So 32 divided into 10. 3.125 times 10 to the minus 1.
3.125 times 10 to the minus 1 moles.
All right. So, how many moles of CO2 can this produce? This one. Right? Get rid of oxygen, leave us with CO2. So that's 2, and that's 3. So 2/3 of that number would be the amount of carbon dioxide based upon all of the oxygen. 3.125. Wait a minute, let me check. See, did I do that one right? 10, that's a third. Yeah, that's right. And 2 times 3 divided. So that's 2.08 times 10 to the minus 1.
2.08 times 10 to the minus 1 moles of CO2.
How about this one? How many would that produce? Well, this one is 2 CO2 and 1 ethanol. Right? So 2 times this one would be what? 6.73 times 10 to the minus 2.
6.73 times 10 to the minus 2 moles
of CO2. Right. Which one produces the least amount? This one, right here. All of the ethanol is consumed and produces this much carbon dioxide. Okay? So, how much oxygen is consumed? Well, if this is how much you have to begin with, and the ratio is 3 to 1, then the amount of oxygen consumed is this one times 3. .72. 6.72 times 10 to the minus 2. This is the moles of oxygen used. Right. So if this is the moles of oxygen right here that you start with, what you have left with is this one minus that one. .45 times 10 to the minus 1. So we have 2.45 times 10 to the minus 1 moles of oxygen left over. And now we have this many moles of CO2. 6.73 times 10 to the minus 2 moles of CO2. So the total moles of gas is what? This one plus that one. Which is 3.13 times 10 to the minus 1. Of gas. All right. So that's how many moles of gas that you have at the end of the reaction. And we just need to convert that to volume. Okay. So I'm going to have to erase some of this so that I can do that calculation. So pressure, volume, moles, gas constant T. We need to know volume. So the moles is 3.13 times 10 to the minus 1. Gas constant And temperature. What's the temperature? 25 plus 273 is 298. Okay. And pressure is what? 1 atmosphere. Okay. This one times 0.08206 times 298 is 7.64 liters. That's how much gas you have. Well, let's see. I make a mistake. I must have made some kind of mistake, because that's a long way from the answer. Of course, the best answer is 6.82. But what mistake did I make? I don't see where I went wrong. Oh, 0.2789. That's a different number than I got here. All right, the procedure is correct. I just made a math error somewhere. All right, in the interest of time, go back and see where I made my mistake. Let's see. Let's go back to one. Go back to 8 or 2. 8. Hydrogen peroxide decomposes to form water and oxygen. Suppose 145.9 grams decomposes and all the oxygen gas is collected in the balloon. Determine the volume of the balloon. Okay. We can do that really quick. So let me see. I skipped also number 2. Let me see if number 2 is going to take more time. 15 grams of nitrogen and 15 grams of hydrogen in a container. Either one. Yeah, either one will work. So let's do 2. Then we'll come back to 8. All right. So here's our balanced equation. Okay. And we start off with 15 grams of nitrogen gas and 15 grams of hydrogen. All right. The original volume of the container is 11.4 liters. There we go. What's the volume after the reaction has run to completion? All right. Assume constant temperature and obviously constant pressure because the piston is movable. So what we need is, we've got before volume and we're looking for after volume. So we need moles of gas before. Then we can get moles of gas after. And once we have that, we can solve that Avogadro's equation.
Okay, so what do? Well, we find out
How many moles of gas do we have to start with?
right, because that's related to 11.4 liters.
So 15 grams of nitrogen is what? Well, dinitrogen would be
28.02. 2 times 14.01. So the moles of nitrogen gas here
is 0.535.
Okay,
Hydrogen gas.
that would be 2.02 for dihydrogen. .43 moles. All right,
Which one's limiting?
it has to be this one. If you need 3 for every one,
Then 3 times that is about 1.5. Right. So
that's what you're missing. So we got this plus that is the total moles,
7.96. So how many moles do you have afterwards?
Well, this is limiting, right? That's limiting. So it's going to be converted into that. For every one of these, you get 2 of those. So this is going to yield
0.535 enter 2 times
1.07 moles. Okay? All of this is gone. Some of this has been used.
3 times that has been used. 1.605.
From 7.43 is 5.83. So that remains. This plus that is the final number of moles. So 5.83 plus 107 is 6.90.
Now all we have to do is solve the equation. Right?
V1 over N1 equals V2 over N2. We're looking for V2, so V1 times N2 over N1 equals what? Well, we have to put the numbers in. 11.4 liters times 6.9 moles divided by 7.96 moles.
And that's the new volume. So it looks like the volume went down. And that makes sense. If you got 1 plus 3 is 4, it goes down to 2. So we decreased the volume. .88. And let's see, that was number 2. Close enough. 9.87 is the final volume. Okay, I've got 20 minutes, I think. Yep, 20 minutes.
So we'll tackle number 8 now. I skipped another one too. I don't know if we're going to get to it, but I'll try.
Let's see. So let's go back to number 8. Here we go. Hydrogen peroxide decomposes. and that's a liquid,
aqueous actually, decomposes
to form
water plus oxygen.
I think I need a different marker. All right. So what are we given? 145.9 grams of hydrogen peroxide. That's a lot. Decomposes, and it produces everything over here. All of it is decomposed. So we just need to find out how many moles of that are produced from this many grams. Notice they're
Actually, there's 2. Sorry.
2 to 1. So how many moles here? Half of them are oxygen.
So let's do that first. Hydrogen peroxide.
So what's the molar mass of hydrogen peroxide? Well, 2 oxygens is 32. 2 hydrogens is 1.01. 34.02. Divided into 145.9. 4.289
moles. So the moles of oxygen like that.
So 2 into that value divided into it is 2.144.
That's how many moles of oxygen.
Okay, so we have moles of oxygen, we have pressure, we have temperature, we can find volume.
So moles is 2.144.
Temperature is what? 25 plus 273, that's 298. And pressure is 1 atmosphere. Okay, so what's the volume? 2.144 times 0.08206, 298 is 52.4 liters. Okay, 52.4 liters right there. All right. Let's see, that was 8. Let's see, which one did we skip? I think it was 30. We got a couple minutes. Maybe we can get that one in too. 30. Nope, it's not 30. Oh, maybe I skipped over it. 79. Here we go. So let me put it in fast forward. There we go. 79. Okay. There we go. 79. All right. A gaseous compound containing carbon and hydrogen was analyzed and found to consist of between 80 and 90% carbon. At 145 degrees Celsius in 1 atmosphere, the density of this compound is 2.45 grams per liter. What's the molar mass? All right. This one requires some algebra. So it wants to know molar mass, correct?
Molecular weight equals mass per moles.
What else do we know about gases? Well, in this case, we know the density.
Density equals mass per unit volume.
And we also know the gas equation.
PV equals nRT.
We know those three. If we want to know the molar mass, we have to keep this one right here. Don't mess with it. So we could substitute some things in here. Right? What do we know?
Well, we know mass. We know the density, right? We got that. And we can solve for mass equals density times volume. So we can substitute this one in here. And over here we know moles. N equals PV over RT. So we can substitute this one in here.
So let's do that.
The molar mass is going to be equal to density times volume divided by N, which is PV divided by RT.
Okay?
So now,
remember, the denominator of the denominator is the numerator.
so this would be D times V RT. That flips up into the numerator with PV on the bottom.
Now we got V on the top, V on the bottom.
Cancel that one. So now what we have is molecular weight equals density times R times temperature divided by pressure.
Now, let's look and see if we have the information we need. We need density. Yep, 2.45 grams per liter.
We know R.
How about temperature? 145.
145 plus 273, right? And pressure.
What's the pressure? 1 atmosphere.
1 atmosphere.
So it looks to me like we didn't even need this 80 to 90% carbon. That was just blue smoke blown right in your face. This should give us the molar mass. In what terms? Well, it has to be grams per mole, right?
This is grams per liter. Grams per liter. So there's grams. Liters is canceled over here. Atmosphere is canceled there. K is canceled here. Leaves us with
grams per liter. Okay, 2.45, 0.08206 times that, and 145 plus 273, 418K times that. So I get 84.0
grams per liter. Grams per mole. It's not grams per liter, it's grams per mole, because liters cancel over here. Liter atmospheres per mole K. Liters cancel, atmospheres cancel, temperature K cancels. That leaves you with grams per mole.
Let's see, is that there? Yep, there it is right there, 84. Okay? So we had to do some algebra here to figure that one out. You had to combine these three equations.
Okay, I think that's it. I'll take one last check to be sure I didn't miss any that I had
previously marked for review. Let's see, 79.